So far, we have dealt with integrals that are simple integrals and then integrals with u substitution. We remember that u substitution undid the chain rule. We have not learned how to undo the quotient or product rule. And today we're going to actually learn how to undo the product rule. It might not be obvious that that's what we're doing, but I'll talk to you in class about where that's coming from. This is going to be something called integration by parts. Before I tell you how integration by parts works, let's compare these two integrals that look really very similar. So we have ln of x over x and x ln of x. When I look at these, the only technique that I really know how to use right now is u substitution because these are not functions that I just know an antiderivative of. In both cases, I would probably try to choose u to be ln of x because we remember that picking x to be our u is never helpful because all that does is rewrite the integral in terms of u instead of in terms of x, which is not particularly helpful. So in this first case, I could choose u to be ln of x, du over dx is 1 over x. And so then we get du times x is dx. And this would be the same in both cases. So let's try and rewrite both integrals using this. So my integral on the right, which I'll write in red, or on my left, sorry, becomes ln of x over x times x whoops. Okay, goodness. It becomes u over x times x du. The x's cancel out, so we're left with the integral of u du. The integral is totally in terms of u, so this is excellent. We can rewrite this as 1/2 u squared, and then we can replace the u, and so this is pretty straightforward. We get 1/2 ln of x quantity squared plus c. Okay, so that's easy peasy for the first one. U substitution works great. If we try doing the same thing on this one, again, we would think U substitution, really the only U we could choose is ln of x. So we try this, we're going to get x times U times x du. The problem here is the x's don't cancel out. This would just leave me with x squared U du. We could maybe try like a back substitution, but if we did that, if we tried to solve for x here, we would have to use e, so we would get x is e to the u, so we would get e to the u squared times u du, and that looks even worse than the original expression did. So u substitution is not going to work on this one here, and so we do need another method of integration, and this is where integration by parts is going to work great. In integration by parts, what we do is we identify two things. We identify u and dv. So you have to be careful that your u's and your v's don't look the same. And then we do this expression over here, which looks kind of weird. So let's jump into an example and see how this works. So the first thing we notice is that my u and my dv have to be two things that multiply together to give me the inside of my function here. So I'm going to tell you what we're going to pick here, and then we'll talk about how we pick these. So I'm going to choose u to be ln of x, and the thing that ln of x is multiplied by is it's multiplied by x and dx. So my whole x dx becomes my dv. We notice that dv has a dx in it, and this is okay. This is kind of like dv over dx is equal to x, kind of like what we did with u substitution. Okay, so the first thing that we always have to notice is that these two pieces, the u and the dv, should multiply together to give me what I have inside my original function. Okay, so once we find u and dv, now what we have to find are du and v. So du is just the derivative of u. That will be 1 over x. And we get a dx in here because we think of this like our u substitution. We start with du over dx is 1 over x in this case, and we multiply both sides by dx to get du is 1 over x dx. I usually skip that intermediate step and just go ahead and multiply the dx over. Okay, v is coming from dv. V is the integral of dv. So this should be the integral of x dx, which is 1/2 x squared. Okay, so now we can go back and look at what this integration by parts formula says. The integration by parts formula says if I integrate u dv, which in this case was this thing, then I'm going to get uv minus the integral of v du. You have to come up with how you can memorize this. I remember this is UV, like UV rays from the sun, and this is like voodoo, VDU. You have to think of what's going to make sense for you. Okay, so let's replace things here. So our original integral was our UdV, so that's this integral is going to be equal to u times v. So that's going to be ln of x times 1/2 x squared. I'm going to write that as 1/2 x squared times ln of x minus the integral of v du. So minus the integral v times du. Okay, so now we're still left with an integral that we have to compute. We still have to compute this integral. Hopefully this integral is simpler than our original integral was. So let's see, if I simplify that, x squared times 1 over x will give me x. So I'm just integrating 1/2 x dx. Okay, that's easy. So I'm going to rewrite this piece. The antiderivative of 1/2 x will be 1/4 x squared. And then we still have a plus c. Okay, so that's our antiderivative here. Integration by parts always makes messy answers out, so don't be shocked that our answer is messy. Okay, in this problem, I told you how to pick u. I gave you your u. That's going to be one of the hardest parts about integration by parts is picking your u, but it's actually not too bad. There's a way that we can remember this. So LIPT is the way that I remember this, and the first letter, L, stands for logs. So if there is a logarithmic function in your expression, choose that to be u. So we're going to pick u to be the first thing that we encounter on this list. So in this particular case, we had a natural log, so we picked that to be our u. Okay, if you don't have a natural log, but you do have an inverse trig, then pick that. That's the I on our LIPT. If you don't have a log, you don't have an inverse trig function, but you have a polynomial, pick that. And then keep going. If you don't have a log, don't have an inverse trig, don't have a polynomial, pick a trig function. And if nothing else, choose an exponential function. So let's look. So our examples of logs would be like ln of x, log base a of x. Inverse trig would be like if I have an inverse sine, arctangent, something like that. Polynomials, that could be something like x squared plus 1. Trig would be like sine, cosine, tangent. Exponential will be like e to the x, 5 to the x, something like that. Okay, so let's look at this example here. So if we use LIPT to pick my u, I have x in here. X is a polynomial, and cosine, which is a trig function. So if I look down my list, I don't have a log, I don't have an inverse trig, I just have a normal trig, but I do have a polynomial. So the polynomial is the first thing I found on this list. So u is going to be that polynomial. I'm going to pick x to be my u. Everything else is going to be my dv. So dv is going to be everything else left here. So the cosine of 5x dx. Okay, so now I need to find du, that's the derivative of x, which is just 1 dx. I need to find v, which is the integral of cosine of 5x dx. You actually have to do u substitution on that. It's a fairly straightforward u substitution, so I'll just jump to the answer here. It's 1/5 sine of 5x. Okay, and now we have to put everything together. So I'm going to remind us our formula is the integral of u dv is uv minus the integral of v du. So the integral that we started out with, this should always be the integral we started out with, is going to be u times v. So I'm going to write that as 1/5 x sine of 5x minus the integral of v du. So that's going to give me 1/5 sine of 5x dx. Now we have to anti-differentiate this thing. To do that, we're going to use u substitution again, picking your u to be the 5x. So when we do that, this piece stays the same. When I anti-differentiate sine, I'm going to get a positive out. Well, I'm going to get a negative cosine, so the negative out front will become a positive. I'm going to get an extra 1/5. I'm going to have a 1/5 times a 1/5, so I'm going to get 1/25 cosine of 5x plus c. If you didn't see where I'm getting that from, let me know in class. Okay, I'm going to go ahead and record one more example. If you're feeling a little overwhelmed by this, then skip this example and we can do more of these in class, but I'll go ahead and record this example if you want some more practice. Okay, again, I'm going to start with picking my u. So let's look at my LIPT. I don't have a log. I don't have an inverse trig. I do have a polynomial. X squared is a polynomial. E to the x counts as exponential, so it's the last thing I would choose. So I'm going to pick my u to be x squared. I'll pick my dv to be everything else, which is e to the x dx. Du is the derivative, so that's 2x dx. V is easy in this case. It's the integral of e to the x, which is just e to the x. So when I put this all together, I'm going to get x squared e to the x minus integral. So this is my uv minus the integral of v du is going to be 2x e to the x dx. And oh no, now I have to integrate this thing. This thing actually needs another integration by parts on it because I still have like two pieces that aren't really related to each other via derivatives. So I need another integration by parts on this piece. My polynomial here is 2x, so I'll choose that to be my u, and I'll choose the rest to be my dv. So my du is 2dx, my v is the integral, which is e to the x. So let me kind of just rewrite what I have here. I have x squared e to the x minus, and then I'll put this all in red. So I do u times v, 2x e to the x minus the integral of v du, which will give me 2 e to the x dx. Okay, so I still have one integral left to do here. So let's write this as x squared e to the x minus 2x e to the x. This will become a plus. Antiderivative of this guy is 2e to the x plus c. Whew, that is a lot to do. So we'll get lots of practice tomorrow in class, or today in class, and another day of integration by parts as well, because there's a lot to this.